Okay, good morning, everybody. So what we're going to do this week for Monday and Tuesday is work on, Monday and Wednesday in lecture, is work on reviewing chapters 4 through 6. Wednesday night, of course, is midterm 2. Friday, we move on to new material into chapter 7. This particular slide here is out of chapter 5 notes. I had skipped this particular problem. I think all the other slides had been covered from chapters 4 through 6 other than this one here. Afterwards, I'm going to get into, I think it's quiz 32 and the chapter 4 to 5 review, just to kind of go through some problems from chapters. Hopefully we get through all of that today, but we'll see what we get through today. And then we'll pick some other quizzes or other review problems for next time. If there's any particular questions you have, if there's like some problem you ran into on a practice test, I know there's a lot of video solutions with those, so you may have gotten most of those issues already taken care of. But if there's a quiz that you took that you don't understand, like say quiz 30 or something like that, or if there's a particular problem on a quiz, just screen capture the problem and send it to me. If there's an entire quiz, just recommend a quiz for next lecture, and we'll try to get into that on Wednesday. And so for this particular problem here, we see the enthalpy of combustion of heptane is minus 4816 kJs per mole. That's when water is formed and the reaction in the liquid state. So the first sentence, what we're kind of supposed to maybe take away from this information is that the combustion reaction from chapter 3 would be C7H16 plus O2 forming CO2 and water, and just specifically where water is a liquid. I think everything else we can understand the physical state of. Heptane's a liquid. I don't know if that really matters so much here. The only reason why you really want to know water, gas versus liquid here is that if you're choosing from a table, though we're just given the information here anyways, you just want to make sure to use the proper enthalpy of formation for these substances in these particular states. But like I said, if we don't have to go to an appendix to look up information, then we're just using the information provided in the problem. So anyways, what we might have to then do is balance the reaction. So we're going to need 7 CO2s. We're going to need 8 waters to balance out the hydrogens, and that's going to be 7 plus 4 for 11 O2s. So I think that's right. 14 plus 8 is 22. 11 times 2 is 22, so 22 O's on both sides. And so the delta H of this reaction here as written can be interpreted from the enthalpy of combustion of C7H16. Because the enthalpy of combustion per mole of C7H16 we're told is minus 4816 kJs per mole. There's 1 mole in this balanced reaction of C7H16. So the delta H of this reaction would be minus 4816 kJs. The delta H of a reaction, if you notice, is almost always kJs, not kJs per mole. The kJs per mole is usually included when we're talking about a property of a substance. So the property of the combustion of heptane is 4816 kJs per mole. There's 1 mole, so we're just multiplying this times 1 mole of C7H16 in that balanced reaction. If we, for some reason, had to double the coefficients, we'd be doubling the delta H of this reaction at this point here. So if we had like a fraction for O2 and we had doubled all the coefficients, maybe we'd be multiplying by 2 here instead of 1. And so anyways, what we should be able to write is that the delta H of this reaction would be the sum of the enthalpies of formations of the products minus the sum of the enthalpy of formations of the reactants. What we're ultimately looking for here is the delta HF of C7H16. In fact, this is how you determine standard enthalpies of formation, or through studying combustion reactions. If you remember, we would get an enthalpy like this, or the enthalpy of combustion from like a bomb calorimetry experiment in the laboratory. So the way we tabulate delta HFs in like textbooks that you see at the end of your textbook is predominantly through doing bomb calorimetry experiments. And so we can solve and determine the delta HF of this guy here as long as we know the standard enthalpy of formations of water and CO2 already, and those are given in the problem. So we can write that our delta H of reaction would be equal to the sum of the delta HFs of the products. So that would be 7 times the delta HF of CO2. And we're summing up, so we're adding 8 times the delta HF of water. And again, if we're choosing from a table, we're just making sure to choose water liquid, not water gas. And then minus the reactants, their sum. So that'll be 1 mole times the delta HF of C7H16. And I could be writing in moles here. Gets a little convoluted. because that's how we're going to go from delta HFs and kJs per mole to just kJs. And then I could write plus 11 times the delta HF of O2, but that's defined to be 0. How do we know this? Well, if we recognize O2 gas as the elemental form of oxygen, that's the most stable form of oxygen, then that's the form that's defined to have a standard enthalpy of formation of 0. Remember, a delta HF is forming the compound or the substance from its elements. And so the formation of O2 will come from O2. So O2 gas, of course, has to have a 0 delta HF by definition. And so then usually you're not told this. Usually you just have to remember H2 gas, O2 gas, N2 gas, F2, Cl2. Bromine's a liquid, iodine's a solid. In terms of diatomic molecules, the noble gases are all monoatomic gases, and then most of our metals are metals, or most of our metals are solids except for mercury, which is a liquid. And then lastly, there's a few that are complicated, like phosphorus and sulfur, that usually aren't asked about. And even more complicated ones could be like carbon, graphite, things like that. So there's some tricky elements. We tend not to, quiz you on what the delta HF is of the tricky elements, so just the more common ones. And so I would just leave it at this, and that this would equal minus 4816 kJs. And then what we can do is just plug in our delta HF of CO2, plug in our delta H of water. So let's just do that here. So CO2s, so it's 7 times minus 393.51. And we plus 8 times negative 285.83. So I get minus 5,041. 41.21 kJs minus the delta HF of C7H16 times 1 mole. So 1 mole times this, and that equals minus 4816 still. So then we're going to want to add 5041.21 to both sides. So I get 225. So we have to, do plus 5041.21 to both sides. So this comes out to 225 kJs is equal to 1 mole, negative 1 mole times the delta HF of C7H16. So we're dividing both sides by negative 1 mole. That's how we get kJs per mole out as our unit for a property of our substance C7H16. So I'm just dividing this by negative 1 mole. And so of course that'd be negative 225 kJs per mole. So looking like answer B here. So now delta HFs are properties of substances. They're in units kJs per mole. That's why we're multiplying the number of moles in the reaction times the kJs per mole to go down to kJs. And then our reaction comes out in units of kilojoules. And so we just write the sum of our products minus the sum of the reactants, and then work that out to be our delta H. Yes?
I understand all the problem, but I did not understand the answer. Does it mean by providing 225 kilojoules per mole, I can create a thing?
No, not like the meaning of the number. The utility of delta HFs are if you have a table of these in the textbook, like you see in the end matter of your book. If you have almost every substance you can imagine with a known enthalpy of formation, then you can just write reactions of A plus B goes to C plus D or whatever your reactions are, and then just look up their delta HFs. So you can work out a delta H of reaction. So there's not a whole lot of meaning in why this is minus 225 and not plus 225, or why the magnitude is bigger or smaller than some other magnitude. The number just simply corresponds to when you take graphite plus the proper number of hydrogens to combine them into C7H16, that reaction has a negative delta H. So like the meaning of a delta HF is that you're forming your compound from its elements. So like 7 moles of carbon solid graphite to get our 7 carbons, and then 8 H2s in the form of H2 gas. That this reaction here is the one that has a delta H of minus 225 kJs, and we're forming 1 mole, so that's kJs per mole for our delta HF. And so there's not much of a meaning on why like this is positive or negative. You'll see stable substances can have positive delta HFs, and it doesn't mean a whole lot. It's not telling you that the compound's unstable or anything necessarily. You can see that some compounds like this are negative in their delta HFs, but the utility is if you have a bunch of delta HFs, then you can have a bunch of random reactions that you write in balance, and you can use those delta HFs to come up with a delta H of reaction. And that those delta H's are very correct, that they're not some prediction or approximation, that those would be the exact enthalpies of the reaction. If you could study them directly with calorimetry, you should find. Okay, so there's probably easier reactions we could have chosen for this reaction. If you just imagine, if you know the reaction, and you know all but one of the delta HFs, and you know the delta H of reaction, then you can solve for that one unknown delta HF. We've done examples before where we gave you the delta HFs and we solved for the delta H of reaction. So this is just another variation of that particular type of problem. There's going to be some more chapter 5 problems that come up. I have no idea which chapter you all think is tricky. I think chapters 4, 5, and 6 are all 3 tricky in their own kind of ways. So I think trying to make sure we hit some problems from all of them is useful here in the next 2 lectures. I also thought that since we were in chapter 6, it might be most useful just to go back to a chapter 6 quiz and kind of start here. And so these are the solutions to quiz 32. So this is like daily quiz 32. If you have questions during my solutions, just feel free to chime in. I think we have plenty of time to try to track down whatever questions you might have. And so what set of 4 quantum numbers is not possible for an electron in an atom? So this question here is getting at how our n value has to at least be 1 and then higher in integers upward, so it can't be 0. So it has to be 1 or greater, and can't be a fraction. It can't be anything between 1 and 2, etc. Our L value can range from 0 to 1 to 2 whole numbers, but only up to n minus 1. M sub L goes from minus L through 0 to plus L, and all integers in between. And then M sub S is either plus or minus a half. And I think we almost started with the spin because it was telling you that a orbital could have an electron going one way or the opposite direction. So you get 2 electrons per orbital. And then N, L, and M sub L kind of tell you information about an orbital. N and L is a subshell. And then the N value is telling you the shell. Some vocabulary reminders. So we could talk about the N equals like 2 shell would be comprised of the L0 and L1 subshells. And so those would be the 2s and the 2p subshells. And there would be a 2s orbital. There would be a 2p x, 2p y, 2p z orbitals, 3 orbitals in that 2p subshell. It's kind of how these quantum numbers are relating together. And so the ones that are not possible, like this L value here and B, is not possible because the highest that L can be is 2, so that's impossible here. So B is probably the right answer. And if we just inspect the others, like 3, 0, 0, and minus a half, that's fine. 3, 2, minus 2, plus a half, those are fine as well because we're less than N, we're minus L to plus L, somewhere in that range. So sometimes you're looking for if L is 2, then M sub L can't be 3. If L is 3, M sub L can't be minus 4. So you're just looking for that range of M sub L's to be within the plus and minus L. And so we're good with D as well, 5. So this would be a 5D subshell and some orbital within that subshell and the electron with a minus 1/2 spin. So that's perfectly fine. And then the last one, 2, 1, plus 1, plus a half, that's fine as well. And so B is the only one here that's not allowed. Okay, so the Pauli exclusion principle says every electron in an atom has to have a unique set of 4 quantum numbers. If 2 electrons share the same 4 quantum numbers, those 2 electrons are in the same spot. So kind of like how each of us are in our own chair, electrons have their own spot too. Okay, so which atom below contains the most unpaired electrons in its ground state electron configuration? So this question is getting at Hund's rule, which says that whenever we're filling electrons into equal energy orbitals, we maximize the spin. We use all the orbitals as possible. So for like sulfur, the electron configuration of sulfur would be neon, the nearest preceding noble gas. For a condensed configuration, then we're filling into the n equals 3 shell, so a 3s2 and then a 3p4. So the idea here is that there's one 3s orbital, it takes those 2 electrons, and then our 3p subshell, there's 3 3p orbitals, so we're going to fill in 1, 2, 3, and then 4. So spreading out those electrons into 2 different orbitals, pairing their spins in the same direction, that's the application of Hund's rule. So we get 2 unpaired electrons here. The nitrogen group of elements would all have like 3 unpaired electrons. If you think about it, they're all going to share that NP3 configuration, so they'll have 3 unpaired electrons. So like phosphorus will be in this group here of having 3 unpaired electrons. We saw sulfur has 2. Manganese is like halfway across the transition metal series, so that's going to be really good for manganese having all of its d electrons unpaired. So if we look at manganese, manganese should be an argon configuration, followed by it's filling into the n equals 4 shell, so it'll be a 4s2. And then the d shell is back in the 3, because the first time we have that d subshell is when n is equal to 3, d is L equals 2. So it's a 3d and then 5 across. So we can count scandium, titanium, vanadium, chromium, manganese to get the 5 across the d subshell. We could double check the number of electrons manganese should have, 25, and make sure that we've distributed 25. So we have 18 plus 2 plus 5, so we have 25 electrons distributed. And then when we think of our diagram here, the difference is our 4s, still 2 electrons, just one 4s orbital, but we have 5 3d orbitals. Now, why do we have 5 3d orbitals? Well, one reason is because we do, but then the other reason, or the way you can check this or know it from the quantum numbers, is that this is the L of 2, and the m sub L range is -2, -1, 0, +1, +2. So the 5 m sub L values are telling you that you have 5 d orbitals. You can also see you have 10 elements across. The 3d subshell helps you figure that out too. But so we're going to put our 5 electrons in, all in the same direction, using all of the 5 orbitals. That just helps the electrons spread themselves out into the different orbitals. It'd be better to do that than try to pair them up together. That's going to put the electrons too close together. Electrons repel each other. They're negatively charged. They want to try to get as far away from each other as possible, yet they're still pulled in by that nuclear charge. That's actually Chapter 7's topic, is how that nuclear charge plays a role in keeping those electrons held in place for our atoms. But so we're going to get 5 unpaired electrons for manganese. And so for transition metals, 5 is going to be the most, because we get up to 5, and then we start spin pairing from there. So 5 is going to be the most that we can have. Calcium is going to have 0, because it's going to have a 4s2, both spin paired, so it's going to have 0 unpaired electrons. And then titanium, next to scandium, only has 2 unpaired electrons. It's a 3d2 configuration, so it ends up with 2 unpaired electrons. It's only filling in 2 electrons into that d block. Okay, so that's an application of Hund's rule. And so sometimes asking unpaired electrons is just a way of making sure we have the correct configuration.
Does it mean zinc, cadmium, mercury, they don't have any unpaired electrons?
Yeah, so like if you get all the way to the end, like zinc is a 4s2 3d10. An interesting question for zinc is how many valence electrons does it have? And even some of the ones we just did, we can go through and think about valence electrons. I'd probably say zinc has 2 valence electrons because it has that filled subshell. But then once you fill a subshell, all the electrons have to be spin paired. And so we're going to have 0 unpaired electrons here for things like zinc. In fact, zinc's often called like a noble transition metal. And the same thing with like cadmium and mercury, is that they've kind of filled like the noble gases, their octets, if you will. So they're more stable maybe than other metals in that regard.
One more question.
Yeah.
Shape of the spin, shapes, does it apply to the last one, or it applies to any one of them? How does the shape come into the picture?
The shape of the orbitals, or the
Yes.
yeah, the shape of the orbitals. Like, there's a particular question I saw that's going to come up at some point on just what orbitals look like. I mean, I think just knowing that the p orbitals are kind of like lobes, and like the d orbitals are double set of lobes, is probably the most helpful thing. It's like sort of picturing that if you have s orbitals, and if you just imagine a bunch of layers of s orbitals, at some point you could probably say, well, isn't there some space here that we can use in between the n equals 2 and 3 shells, and that's where the 2p orbitals are using. And then if you imagine kind of going to the 4s, that there, and then you have the same sort of 3p orbitals here, that you notice how there's some growing space in between those 3p orbitals? Like there's a little bit of empty space maybe that's not being used. That's where those d orbitals come into place. The d orbitals are trying to use the space that's in between the p orbitals. And so if you're imagining a set of axes, for example, so you have your axes here. And so if you have your p orbitals aligned on the axes, that most of your d orbitals, or 3 of the 5 d orbitals, are in between these orbitals here. So the d orbitals are going to be in between these orbitals here in their clover leaves. It's a little hard to see once you sketch all 5 orbitals, but the d orbitals are just trying to use space that those p orbitals aren't using. And then if you go to even bigger d orbitals, the f orbitals start trying to find the space in between those d orbitals and the p orbitals. So the orbitals are just really clever. You know, they're just trying to find space that's unused. But I think knowing what an orbital looks like is almost like, we might just say, well, what is this orbital? Like, is it a s orbital, p orbital, d orbital? Remember, the book doesn't actually show f orbitals, so I don't think we'd ever show you an f orbital on a test. I just show them because I think they're kind of obvious on what they're going to look like, just to kind of fill in the gap of making sure we understand why the orbitals take some of their shapes. So I don't think you'll see an f orbital on a test or anything. And then from there, maybe just connecting it back to a quantum number. Like the L of 2 is the d. So if you see a d-shaped orbital, it's going to be an L of 2. But we'll see a question like that in a couple of moments. So I think in terms of shape, it's almost just like recognizing an orbital, but not necessarily thinking, well, what's the shape of an atom with a configuration? I don't think we'd go that deep of a question. So which atom below has 6 valence electrons? And even if we looked at the examples here, like for sulfur, 4s2, 3p4, 6 valence electrons, the outermost shell electrons count towards our valence. So for sulfur, we have 6 valence electrons. And then if we think about like manganese, if we're filling a subshell that's lower than the outermost shell, so the n equals 4 is the outermost shell, so we definitely have these 2 electrons counting towards our valence. But what about these 5? Well, they count too. So if we have a lower n value subshell that's not yet filled, we're counting those electrons towards our valence. And so we have selenium, which is in the oxygen group. And if we know oxygen and sulfur have 6, then we know by default, without even thinking too hard, that selenium should have 6 as well. Like the entire halogen group has 7, the carbon group has 4, etc. And so we could also double check, like we could look at selenium and say, well, it would be an argon 4s2. It fills across the 3d10, then it gets back to the 4p4. And then it's this here doesn't count once that d subshell is filled. Once we put that 10th electron into the 3d subshell, it's not counting towards the valence. So the only outermost electrons here are those 2 plus 4 electrons. So that's how we get 6 for selenium. Molybdenum is after krypton. It's in the 5th row, and it's a 3d, or it's a 5s2, 4d4. So it's a krypton configuration. The next one will be the 5s2. Those are the elements that come next, or in the s block. And then we're 4 across into a 4d4. So 2 plus 4. So this is an unfilled lower subshell, outermost shell for 2. So we have all 6 here for molybdenum. And then ruthenium adds 2 more. So ruthenium is going to have 8. Because ruthenium is going to be a 4d6 on top of the 5s2. And so only A and B have the answer of 6 valence electrons that the question was asking for. Yeah, 1 second. Yeah, what's up?
For the selenium, S is bad. Why are we having it as a valence electron?
Say that again?
For the selenium, you said 6 only for 2 for S2
Yeah? Oh, so the valence is the outermost shell electrons plus any lower subshell. So it's not the highest subshell, it's the highest shell. So the shell is the n value. So the highest shell, that's a good question, is the 4. So remember, the n value defines the shell. And so the outermost shell electrons are the n equals 4 for this atom. So it's going to be the 4s and the 4p.
Which means the 3D will never come into the picture at all.
The 3d10? Only if that's then unfilled. So like when we look at what I was kind of erased here, let me put this back in. So for molybdenum, 5s2, 4d4, like when that 4d isn't filled with 10, then we count the 4. But notice how that's a lower subshell than the outermost shell. So the only thing is, like if you're thinking of valence as the outermost electrons, as the outermost shell, you have to expand that word shell when you have a lower subshell that's unfilled. So it's like a tricky statement to fill, or to ask, or to word. But outermost shell plus any electrons in a lower unfilled subshell. Yeah. So how many electrons in the ground state configuration of chlorine have an angular momentum quantum number L of 0? This is like a trivia question. This is like one of those like silly questions of, okay, if you do the full, like it might be wise to do the full configuration here, like a 1s2, and we're doing this for chlorine for 17 electrons. So 1s2, 2s2, 2p6 gets us through neon, 3s2, 3p5 gets us to chlorine. So that's 2, 4, 10, plus 7. So that's 17 electrons. And so this here, you know, this looks like neon, the neon configuration, and this is 3s2, 3p5. And so when an L is 0, what does that mean? Well, an L of 0 is the s. So that's an s orbital. And so we have a 1s, a 2s, and a 3s. So this is kind of a trivia cell question. It's like, for this atom, 3 of its orbitals are in s orbitals, and there's 2 electrons in each of those. So how many electrons in chlorine have an angular momentum quantum number L of 0? The answer would be 6. So it'd be the 1s2, the 2s2, the 3s2. And so these questions here are just really connecting configurations to quantum numbers to then just like asking a trivia cell question. Yeah.
On one of the reviews, it was much more like irregular,
Anomalous.
yeah, like where it was like S1 and then P4.
Yeah.
Something that we should look into.
Yeah, so in terms of the anomalous configurations, like some configurations, not really in the S and P block, but more in the D block and the F block elements, will have electrons that move from one subshell to another as the most stable configuration. Like chromium was one, where instead of being the 4s2 3d4, it was like a 4s1 3d5. One, you don't have to memorize those that do that. Two, it's not very periodic anyway, so it's really hard to predict those trends. And then just sometimes it comes up. So I would just like understand that in the D block, that there's sometimes the S block similar in energy, you can move electrons around. Sometimes there's more stable configurations than the orbital energies we tend to think of them in. And then if we give you a configuration, you can tell us the element just by counting the electrons.
Okay.
And so for the most part, it's atom to expected configuration or a configuration to the atom is kind of the idea. And so predicting which elements have an anomaly, I wouldn't worry too much about that aspect. Okay, which element has the anomalous configuration? Like this question here is kind of getting at that type of question. So we're told here that this element's anomalous. It's not the expected configuration. Because we would have expected this element probably would have been a 5s2, 4d6. You know, right? We would have filled the S block with 2. So this would be our expected configuration. But then it turns out that it's anomalous. It just moves 1 from the S into the D. So we don't destroy or add electrons. We just move them around from one subshell to another. And so if we're asked a question like this, we're really just saying, well, what's the 8th element across the 4th row? So like which element has krypton's 36 electrons plus 8, so that would be 44. And this, we're not doing ions in this chapter, so everything's neutral in charge. And so we're just looking for the 44th element, which would be ruthenium. And even in the book, it talks about how, oh, usually like a half-filled subshell is more stable than a fully filled subshell. Like a lot of times you get anomalies when you're half-filling the D or when you're totally filling the D subshell. But here, like ruthenium and rhenium actually have these goofy configurations where they're forming like a configuration you would never have expected would be the anomalous configuration. So there's something that's especially more stable about this configuration than that 5s2 4d6, and that this is the most stable configuration for this element. So this would be ruthenium.
The other elements in the same group, like the iron and OS, also have the same thing?
No, that's what I was mentioning earlier, is that it's not, often this is not periodic. You know, and it's often very troubling. So so ruthenium does this, but rhenium and osmium don't. Or iron and osmium don't do the same trend. Like, it gets even more confusing. Like, molybdenum and chromium have an anomaly, but then tungsten doesn't have that same anomaly. And it gets even more wacky. Like, the nickel, palladium, and platinum each have a different anomaly. Like, copper doesn't do it. Silver moves, I think, 1 electrons, nickel is not anomalous, it's the expected configuration. Palladium, I think, moves 2 electrons over into the D block, and then platinum moves just 1 over. It's very peculiar on the periodic trends here on why the elements behave the way they do. So yeah, don't worry about periodic trends with these things here. It's often not periodic. Yeah. The other thing that's not so obvious is that when we talk about a configuration, it's really for like it's like they dust this under the rug, but it's for a gaseous element. It's really not for like a block of iron metal that necessarily has this configuration. It's for like an isolated atom of these elements, like if it's existing in the gas phase, and these are their configurations. Like when atoms form together, they can pair their electrons together and form metallic bonds in peculiar ways that we're not really describing here. And so one thing that may not be so obvious is that we're talking about isolated atoms with these configurations and not them in necessarily their solid form. Okay, so 6, what is the maximum number of electrons in an atom that could have N4 and M sub s minus a half? Okay, another trivia style question. So N equals 4. So the N equals 4 shell could have L equals 0, 1, 2, or 3. Would be the range of L values possible when N is 4. So we could have the 4s, 4p, 4d, and the 4f subshells. And so if we start thinking about the total number of orbitals, we'd have 1, 3, 5, and then 7. For the 4f, for the 4d, for the 4p, and the 4f. And so if we're counting 1 plus 3 plus 5, that's 9, plus 7 is 16 orbitals within the entire N equals 4 shell. And so then there can be 32 electrons in these 16 orbitals, and 16 of them will be spin up, 16 of them will be spin down. And so we're going to have a maximum of 16 electrons that can be spin down in these 16 orbitals. So 32 total, but then 32 electrons, and then half of them will be spin up, half of them spin down. And so again, this is just connecting the idea of orbitals to quantum numbers, to the meaning of those quantum numbers and the range of their values. Question 7 is getting at the question I was alluding to earlier. From like looking at the shape here, a single set of lobes would be a P, but then this extra ring here is showing us that we have sort of like two like sort of planes of no probability. That's the definition of a d orbital. So this was one of our 5 d orbitals. 4 of them look like clover leaves, and then 1 of them look like this donut ring orbital. So this is one of the d orbitals, and then a d has an L of 2. So the angular momentum quantum number L for this orbital here would be 2. Now, sometimes a question could say, well, what's a magnetic quantum number consistent with this orbital? So what could be an M sub L here? Well, the value could be -2, -1, 0, +1, or +2. That it could be any of these. So like the orbitals, it's not as if one of the m subbals is defined to be one of the particular d orbitals. That just like a d orbital is one of the m subbals. And so the same thing if you imagine like px, py, pz, one of them is the m subbal -1, one of them is the 0, one of them is the +1. And yeah. Well, it's just getting at the m sub l range is just -l through 0 to +l. So it's just like a different variation of this question could have said, well, what's the range of m sub l values that are possible for this orbital as opposed to the L value?
Oh, I didn't even understand the answer to the problem itself.
So the problem here is getting to look at the orbital to determine that it's a d orbital first. So as long as you determine that it's a d orbital, then the question is, well, what would the L value be? If it's a d, the L has to be 2, because that's the definition of d. Because remember, L0 is S, L1 is P, L2 is D, L3 is F. So like those shapes are coming from the L value. So again, it's just picking up that it's the D shape, L has to be 2. And then, like I said, F, I don't think we would show you the F shapes again, predominantly because the shapes aren't even in the book. I just found them in some other source to add to our notes so that you can see what they look like. Consider the electron configuration of vanadium and determine how many unpaired and valence electrons the atom contains. So for vanadium, the configuration here. And the question like this, sometimes you may get confused. When you write argon, 4s2, 3d3, you might start getting confused of thinking, well, do the 2 electrons move over and this has one of those anomalies? We would probably cue you into that. We would say something like vanadium has an anomalous configuration, or that it has one where all the s electrons move into the d subshell. We would give you information. We wouldn't just tell you some element like molybdenum that is anomalous and expect you to have that memorized. And so, in fact, vanadium doesn't have an anomaly. This is the configuration of vanadium. And so just because you can conceive of electrons moving from the s into the d subshell doesn't mean they do. And so this is the configuration here. So we have a 4s, 2 spin paired electrons, and then our d5 orbitals, we have 3 unpaired. And so we have a 3d3 configuration. So we have 3 unpaired electrons. And then we have 2 plus 3. So we have a total of 5 valence electrons. So unfilled D subshell counts and the 4s subshell counts. Question 9, which transition to the H atom requires the least amount of energy to be absorbed? And so we're absorbing energy when we go up from low end to high end. We emit energy when we go down from high end to low end. So when we're thinking of 1 to 2 to 3 to 4, as we go upward, that the energy required to successfully go to the next higher end is getting smaller and smaller. In fact, this is good because if not, it would take an infinite amount of energy to ionize an atom. So at some point, we can ionize an atom. So if we get to n equals infinity, that's the ionized atom. And so it'd be good if the electron could at some point fall off the hydrogen atom. I don't know what the world would look like if it couldn't, but if you're thinking of the energy, it's really one of 3 possibilities. Either these energy levels are going to be equally spaced, that's not the case, or they're going to be successfully increasing in energy each time, that's not the answer, or they're going to be like this where each time it gets a little bit lower in energy to successfully go up to a higher n value. And so we're going to have a big energy from 1 to 2, lower energy from 2 to 3, lower energy from 3 to 4 to have the atom increase its n value. And so the least amount of energy to be absorbed, 1 to 2 versus 2 to 3, well, 2 to 3 is going to be better than 1 to 2. 1 to 3 has got to be a higher energy. If we go from 1 to 3, it has to require a greater energy than just the 2 to 3, so we can roll 1 to 3 out. 3 to 2 is an emission of energy. 2 to 1 is an emission of energy, so we can roll those out. So those don't involve the absorption of energy, these involve the emission. So these ones here are both relating to emission. of energy, not the absorption of energy, so that's why they would be wrong. So the least amount of energy to be absorbed for the choices here would be for C, 2 to 3. So it's really just getting us to imagine if we know that 2 to 3 are closer together in energy than 1 to 2. Then 10, which of the following statements is true for a 5d orbital? The electron can have any principal quantum number 0 to 5. The magnetic quantum number may be 0. The magnetic spin may be 0. The magnetic quantum number must be 4. None of these are true. Well, let's deal with the magnetic spin first. It's either plus or minus a half for every electron, so it can't be 0. And so this is incorrect. We're looking for which statement is true, so C is definitely wrong. For an electron in a 5d orbital, its n would be 5, and its L would be equal to 2. And so the principal quantum number could not range from 0 to 5. It has to be 5. So it's not ranging from 0 to 5. In fact, it would probably range from 1 to 5. But its principal quantum number, n, would be specifically only 5. The magnetic quantum number is the m sub L, is magnetic quantum number. And it could be -2, could be -1, could be 0, could be -1, could be -2. So it can range from -2 to -1 to 0 to +1, or it could be +2. So it has to be one of those 5 numbers, but only one of those 5 numbers, but not necessarily all of those numbers at the same time. So just one of those numbers. So the magnetic quantum number may be 0 is true. So the m sub L could be 0. That's one of its ranges. And then the magnetic quantum number must be 4 is wrong because that just, it can't even range up to 4, for one. And then 2, I think the reason why this answer is here is if you imagine n being 5, there could be an L equals 4 orbital. That's just not a 5d orbital. This would be like actually a G orbital, right? So what comes after F is G. This would be a 5G orbital could have that quantum number, not a 5d orbital. So I make that statement incorrect. And so then it's not asked, but the angular momentum quantum number L would have to be 2, and only 2, and not 0 or 1 or 2 or 3 or 4. Okay, so that just kind of connects it.
A D again, I thought about it as
Yeah, the D just means L is 2. And so then that tells us our range of m sub L's from plus L to minus L.
what is D exactly? I thought about it and didn't get it.
Well, the thing is saying consider a 5d orbital. Which statement is true about the electron in the 5d orbital? So the n would be 5, the L would be 2, the range of m sub L's is -2 to +2, so it has to be one of those numbers, and then the spin is either plus or minus a half.
I get the answer down. You were saying something about the 4.
Oh, yeah.
I remember before something that happened.
Yeah, if the m sub L is going to be 4, then the L has to be at least 4. And if the L is 4 or greater, then the subshell would be G or greater, which is just not this subshell. Yep. All right, so I think we're going to go back to chapter 4 here, and then progressively get into some chapter 5 questions. This is a chapter 4 to 5 review set on Carmen. And so which substance below, when mixed with nitric acid, would lead to the formation of a salt plus water? And so HNO3, of course, is an acid. So an acid plus base lead to a salt plus water. So we're looking for the base. KOH would fit the bill. So that should form the salt of KNO3 plus water. Silver plus acid could react, but it doesn't necessarily form a salt plus water. Remember, that would be a oxidation reduction reaction. An activity series would be helpful, but silver is less reactive. It's not going to react in acid anyways. H3PO4 is another acid. Two acids don't really react together to form any salt plus water, so that's not going to react. Calcium can actually react, and if we think of an oxidation reduction reaction activity series, so calcium would be here, our H plus or H2 going to 2H plus 2 electrons below. So this reaction here can take place where calcium metal is going to dissolve in HNO3 to form calcium nitrate AQ, and then plus H2 gas. Something's out of balance here, but so okay, so this reaction here would take place. This is from section 4 of chapter 4 in oxidation reduction reactions, but the key is you get a salt, but the byproduct here is H2 gas, not water. So we're really just looking for acid plus base goes to a salt plus water here, so the only answer here would be KOH. And so calcium can react. We can think about the reaction. It's the oxidation reduction reaction. We can look at the calcium losing electrons being oxidized, the hydrogen gaining electrons being reduced in this reaction, and it being an interesting reaction, but just not a possible answer for this question. Which compounds below are a strong acid? Now, we just have to memorize the 7 strong acids, and in case you forgot, we have HCl, Br, and I, HNO3, so nitric acid, HCl3 is one of them as well, ClO4, and then the only diprotic, but only for the first H, is H2SO4. And so H2SO3 is going to be weak because it's not one of the 7 strong, and HClO3 is one of the 7 strong. So only one here, only chloric acid is the strong acid. So the implication is sulfurous acid must be a weak acid if it's not one of the 7 known strong acids. So if we know how to recognize and name something as being an acid, and it's not one of these 7 strong acids here, then it is a weak acid, is the idea. So what is the best term to describe acetic acid in solution? So acetic acid with the given formula. Now, does it lose just the one H or multiple hydrogens? The answer is just the one. Now, you may wonder, how do you know this? Well, one reason is that we never learned how to name the compounds if we lose the H. Think about it that way. Like, if we had those hydrogens lost from acetic acid, we would have no way of knowing how to name that compound. The reason why we don't know how to name that compound is those hydrogens stay intact. The same reason why in like methanol is neither an acid or a base. Only ammonia is a weak base, and then the other bases are strong bases that are like metal hydroxides that are soluble in water. And so just because a compound has hydrogens doesn't mean they spontaneously give off in water and are lost. And so this is neither an acid or a base, and only this H here is acidic. And you can imagine if the other hydrogens were acidic, we would have had to learn how to name those things back in chapter 2. So it's through a little bit of circular reasoning you may come up with that acetic acid is not one of the 7 strong, so it's weak, and then monoproduct because it only loses one H. And then if we ask us about methanol, it's neither an acid or a base. And so for like something like methanol, neither an acid or a base. And you can think about it from perspective, does it have the name acid in its name? Nope, well, it's not an acid. If methanol behaved as an acid, we would have called it an acid back in chapter 2. So you have to have a little bit of circular reasoning on like the reason why we call things acids is because they behave as acids, and the things we don't call acids don't behave as acids. And then ammonia is really our prototypical 3 things bonded to an N, or really just NH3 is about as deep as we go in this class here, because it's a little bit hard to come up with structures to know when you have 3 things bonded to an N before we get through chapter 8. Which compound below is a weak electrolyte and weak base in aqueous solution? So weak electrolytes partially dissociate to ions. Weak base are where that dissociation happens to form OH minus. And so copper hydroxide is insoluble in water, so it's neither an acid or a base in water. Sodium hydroxide completely goes to Na plus OH minus, so this is a strong electrolyte, strong base, because we get the complete ionization of sodium hydroxide. Methanol, we just talked about, doesn't do either acid or base reaction, so this is a non-electrolyte. So neither an acid or base. So it's not an acid or a base. And then, of course, by process of elimination, ammonia should be the answer, but it's the answer because ammonia reacts with water to form ammonium plus OH minus. And this again through a little bit of just knowing it, but that ammonia just does this partially. It doesn't do a complete reaction to NH4 plus and OH minus. And so ammonia here is a weak electrolyte because we're only partially making ions, and then one of them happens to be OH minus, so we call it a weak base. Question 6, the conductivity of solution is directly proportional to the concentration of dissolved ions. When you have a mole of each of the compounds dissolved in the 10 liters of water, which compound has the least conductivity? So least conductivity is going to be the solution with the least number of ions dissolved into it. And so KF is a strong electrolyte, water-soluble ionic compound. Anything with potassium is water-soluble. Ammonium, we just saw, is a weak electrolyte. Lithium carbonate, anything with lithium soluble, it's one of the exceptions for carbonate as well, so this is a strong electrolyte. And then sodium nitrate is also a strong electrolyte. And so we get a ton of ions with A, C, and D. We get very few ions dissolving with ammonia because of it being a weak electrolyte. So here we're getting 2 ions per mole of KF. We're getting, for C, we're getting 3 moles of ions because we're getting the 2 lithiums and then the carbonate. So we're getting the 2 lithiums plus the carbonate ion, and then we're just getting 2 moles of ions with sodium carbonate. And so the least conductivity has to be the weak electrolyte because it's only partially making ions. We're getting less than 2 moles of ions. Yeah. Well, through a little bit of memorization of ammonia just being the prototypical weak base, weak electrolyte, and then the others just from being ionic compounds and then thinking about their solubilities. You can check the solubility chart if you have to. Just remember, this one's not on the chart, that the alkalis in ammonium are always soluble. So anything paired up with an alkali cation or ammonium is soluble, so that's why KF is soluble. And then the others are exceptions that are on the chart, or that you get from the chart. And so, yeah, so if the question had asked for the greatest conductivity would have been solution C, right? So that would have had the most ions per mole. Let's see if we can finish this page. We'll see if we come close to that or not. So which statement below is true? All water-soluble compounds are strong electrolytes. That's not true. All water-soluble ionic compounds are strong electrolytes, but not all soluble compounds in general. All ionic compounds are water-soluble. That's not true because we have insoluble ionic compounds and soluble ionic compounds. All strong electrolytes are ionic compounds. That's not true either because our strong acids are strong electrolytes in water, and those are molecular compounds, like HCl, HBr, et cetera. Those are molecular compounds, so that statement's not true. And then the last one, all water-soluble ionic compounds are strong electrolytes. And that's exactly a true statement. So if an ionic compound is water-soluble, it has to dissociate into its ions. And that's the process for it dissolving into water, is water forming like a sphere around each ion separately. And so like NaCl only breaks its ion forces of attraction in the solid by replacing them with water interactions. So ionization has to be the process by which ionic compounds dissolve in water. Question 9. So if I have 30 mils, I just know this one's going to take more than a minute. Let me see if there's anything. Let me do question 10, and we'll circle back to 8 and 9 next time to start. But oxidation numbers. So our oxidation numbers are usually looking at like hydrogen's +1 with non-metals. It's only -1 with metals. So it's +1 here. Oxygen's -2 with some exceptions, and the exceptions are thinking, is this a peroxide or superoxide? Well, these aren't O2s paired up with like lithiums or sodiums and things like that. And then also a compound with fluorine. There's no fluorine here, so I don't think this would be an exception with fluorine. So it's just the ordinary -2. And so we have +2, -2. The overall charges have to sum to 0, so the oxidation number of carbon has to actually be 0. For 0, +2, -2 to go to 0. Okay, so we'll pick up in some chapter 4 and then some chapter 5 questions on Wednesday. All right, guys, have a great day.